Hello, my steel design friends. In the last video, we started talking about the different states of stress on flexural members or on beams and kind of the evolution of, the definition of first yield and fully plastic. In this video, I'm going to show you what you can do with that fully plastic calculation, that MP moment, by studying collapse mechanisms and what we call plastic hinges. So without further ado, let's get started. So a plastic hinge is basically, if you remember back in our original video, when we were talking about the state of fully plastic, we were looking at a stress state that looked like this, where the entire cross-section had reached this limiting stress of Fy. There was no additional capacity that could be applied to this beam. So the idea of modeling this as a hinge is somewhat valid, because if I put any more load on it, this is unable to resist that load. And if it can't resist the load, then what will happen is that member will start to kind of rotate relative to the point that is experiencing this stress state. And so that's kind of a hinge-like behavior. Now, it's not a true hinge in the sense of a mechanical hinge or a connection like a roller support or a pin support, but it does functionally, once you reach that limit, and there's no additional capacity, it's free to rotate after that point. So this is what we're going to take advantage of today. All right, so the way that this works is that basically we take a beam, and I'll show you a bunch of different examples for simply supported and fixed and even continuous beams, and start to kind of show you what we can do with this. So we're looking at plastic hinges and what we call a collapse mechanism. Now the first assumption I have to set up right away that we do this is we are assuming that this beam is laterally braced fully, that it's got some sort of slab on it that prevents this beam from wanting to roll or to otherwise not move in a vertical plane. Okay, now we'll get into some phenomena later on here in a couple of videos from now called lateral torsional buckling, where that is not the case. This method does not work for those. Okay, so we're going to basically take a look at this as being fully laterally braced. So that's why I have a note, that's why I've starred it, that's why I've boxed it. That is a critical assumption for what we're about to do. Okay, all right, so here's what we're going to look at. So let's take a simply supported beam with a point load somewhere in the middle. If the load is fairly small, this beam can hold it and it's stable. But if I increase the load, at some point I will reach that Fy stress state, that plastic stress state that we saw here. My section at the middle at the peak moment will look like that. At that point we have a hinge that will occur, and most likely, since this is the peak moment occurs under this point load on this particular beam. Now it doesn't always, but on this one it does. That if that hinge forms, and you'll notice that I have, you'll see me putting black circles under here to recognize that that is a plastic hinge that is formed. If I have a pin support here and a roller support here, and I put a third hinge in the middle, this becomes a failure mechanism. Three hinges is an unstable structure. Okay, that any other load or anything else that happens to this beam will continue to deflect. All right, now what we're looking at is, so the collapse mechanism on this is I have a real support, okay, which is a real hinge. I have a real roller, which is also a real hinge. It's free to rotate by definition. Okay, and then I have this kind of artificial hinge, this plastic hinge, that once I add it will cause the beam to fail. That's the mechanism. It's a three hinge mechanism that causes this guy to fail. Okay, now what's happening at this hinge is the MP moment is the moment that is occurring here that's causing that to occur. Okay, and so we'll take advantage of that with some energy calculations here in just a little bit. All right, let's go take a look at another one. Let's take a beam that is fixed on this end and is pinned at the left end, and I put a point load here. Okay, well then the collapse mechanism for this is I have a real hinge there, okay, because of the pin support, okay? But if I form a hinge at the wall, which would be where another high moment would occur, and I form another moment or another hinge underneath this point load, now I've got that three hinge mechanism. So this one, if I have two additional hinges to the one I already have, then that would also be a failure mechanism. And I'll show you how to work with that once you've identified where these hinges are located. Okay, so let's go take a look at then a continuous system. Okay, for this one, let's assume it's a continuously supported beam, and I'm looking to put a point load in the middle span that's in here. Well, clearly there are no internal hinges. This guy doesn't count and this guy doesn't count, But to fail this span of the beam in flexure, if I formed a hinge over this support and over this support and underneath that point load, that would be a 3-hinge mechanism. Okay, and so I would have to form 3 plastic hinges on this cross section in order to cause that section to fail. Okay, now in one of the later examples, I'll show you that sometimes we don't know which mechanism is going to control, and so we have to do several analyses, but it's all very easy and very straightforward. Okay, so let's go through and let's kind of take a look at how we can kind of reason our way through it. And I'll go to the most complex case for now, and that's this 3-hinge mechanism, but I'll kind of chop things up a little bit. And so what I've got is I've got a fixed beam, okay, that has a point load in the middle at some distance A from the left and B from the right. Okay, I said the length is 18 feet. That really doesn't matter. I'm not going to use the 18 feet, so we'll just take that off of there for now. We'll just call it as L, okay, for what we have happening on this. All right, so the first thing we do is we figure out what is my mechanism that will cause this beam to form a 3-hinge mechanism. Now, obviously, there are no real hinges in this, so I obviously have to form a mechanism by putting a hinge here, a hinge under the load, and a hinge over at the support, and that's what I did. Okay, now the way that we start to analyze this is we say, well, all right, when this thing starts to fail in the collapse mechanism, that hinge that's in the middle will move down some amount that we're going to call as delta. Okay, now we don't know the amount. It depends on a lot of things. It depends on the load. It depends on the moment. It depends on the geometry of the section. You know, a whole slew of factors. But we know that it moves somewhere. So we're just going to leave it as delta because it won't matter in our discussion. All right. So when that delta forms, there is an angle that occurs at this left point that we're going to call as theta 1. And all we're doing is straight lines that connect the dots. So the first line is the one that goes from hinge A down through the point at B and continues on. And we're going to say that that is, no, originally the beam was horizontal and it wound up here. So it moved through a rotation of theta 1. All right. And then likewise, when this point comes down, because that was the support, then this line, you know, started out here, it will end up here. And we're going to call that angle that it moved as theta 2. Okay. And then we're looking at the magnitudes of the angles. So the rotation that this point had to go through in order to achieve its plastic mechanism was an amount of theta 1. Now, and the amount of rotation that C went through was theta 2. And again, that was an MP moment that caused that hinge to form. But I also get an MP hinge here. How much did it go through? Well, originally, the beam was flat. Okay, but now the left side is doing this and the right side is doing this. The rotation that it went through is that whole thing. And if you look at the math, that is the value, the magnitude of this angle is theta 1 plus theta 2. So that's what we're going to set up for that. Now, if we kind of look at some relationships, we can write that, well, this delta equation in the middle, he's common to both sides, right? And that theta 1 times A is delta. So that's the first formula. And theta 2 times B is also delta. So if I set these two guys equal to each other, you can see that theta 1 is equal to theta 2 times B over A. And so I can actually figure out what the relationship of these angles are relative to each other. And then with that, I can start to kind of do some analysis. Okay, now here's what we're going to do. We're going to calculate this by virtual work. Okay, now it's not the virtual work you learned about in structural analysis where you put a unit load on things. We're just going to do external work and we're going to do internal work. So it's kind of a work energy kind of calculation. The external work that's done on this beam occurs by the load that's applied that we're calling as Pn, looks like a Pu, but it's a Pn, okay, multiplied by the distance that it will move through during the failure mechanism. So it's going to move through a distance that we call delta. So this is Pn times delta. That's the external work. The internal work is the rotation that takes place inside in the elements, okay, which multiplied by the moment that's applied at that point. So for A, the moment is MP. And so MP rotates through theta 1. So the first term is MP times theta 1 for the internal work. Okay, and then theta 2 will be, or sorry, the second one is our hinge at C, also MP, and it rotates through theta 2. Okay, and then the hinge here at the middle, also MP, but it now rotates through theta 1 plus theta 2. Once I've rotated through all of these, you know, and they may not occur at the same time, but once the third one fully forms, your mechanism is in place and you now have a collapse mechanism. Okay, just remember that we're calculating the work done by a rotation as being the moment at the point multiplied by the rotation that it goes through. Okay, now if we go back and we kind of look at theta 1 and theta 2, there's some interesting things that we can do. So let's take our theta 1 formula and rearrange it a little bit and say theta 1 is equal to delta over A and theta 2 is equal to delta over B. Okay, if I plug in theta 1 and theta 2 into this internal equation, I get something that looks like the following. I'm going to factor out MP because MP is common to all of these. And then I'm going to plug in theta 1, theta 2, and then theta 1 plus theta 2. So that's these three terms. Here's theta 1, here's theta 2, and here's theta 1 plus theta 2. And if I do all of the math on this and I substitute in this, I'm going to also factor out the delta and put the delta on the outside. I get all of this as being 1 over A plus 1 over B plus 1 over A plus 1 over B. And again, this was that second one, or the middle hinge, doing that. And then if I do a little bit of algebra, this internal work is MP times delta times 2A plus 2B over A times B. So not too bad. Now, for conservation of energy and conservation of work, we know that the external work has to be met by the internal work. And we know that W external, that this guy has to be equal to W internal for that. Okay, so external equals internal. And so if I do that, if I plug in, my external equation was Pn times delta, and my internal was this equation over here, this MP delta 2A plus 2B over AB. Look at what happens. The delta is now common to both sides, and it will cancel out. Okay, which means then I can write an equation in terms of the plastic moment as a function of the load that's being applied. And so this is the plastic moment that is needed to resist the load. So MP is equal to Pn times AB over 2A plus 2B. Basically, I take all of this stuff and I take it over to the other side. Okay, and if I recognize that the plastic moment is that formula Zx times Fy, and again, we've assumed that my beam is oriented in the I configuration. If it were in the H, you would use Zy here. Okay, but if that's equal to Zx Fy, well then I can basically solve for Zx as a function of the load, and this becomes the Zx required would be that nominal load times AB over 2A plus 2B times Fy. And that's the way that I can get this. And then with this, I can go to my tables and I can pull a beam that I know will be able to hold the size of the beam. Now again, it depends on the value for Pn. If Pn is really big, this is going to be really big. And if it's really small, it's going to be really small. And of course, the location of the load is also a factor. But that's the general methodology for what we're going to apply for virtual work. Pretty easy and pretty basic. It's kind of a cool little trick, actually. All right, now let's take a look at other load types. Let's take a look at, well, what do I do with a distributed load? Okay, well, it's kind of set up the exact same way. Okay, and so what happens is we're going to go fixed, and distributed load in the amount of Wn happening here. Okay, and so my three hinge mechanism, I'm going to get one that forms at the wall, and I'm going to get one that forms at the location of the maximum moment, which in this case happens to be L over 2 for this scenario. Again, we're looking at pure fixed and pure fixed. Okay, and so what we're going to look at then is that my external work, though, now is basically the amount of load times the distance that all of it moves through. Okay, so if I look at this as being like my deflected curve, I can come in and take an average value here and apply that across the entire length, and I get the same amount of deflection, that would be inside of this triangle that we calculated. So we're going to calculate the total load then, or the external work as being the total load multiplied by the average deflection. Okay, and so that's going to be Wn times L. That's the total load applied. Again, we assumed L was the length of the beam. Look at that on there. Looks something kind of like that. Okay, and then the average deflection, if delta was the whole thing, then the average is half of that. Okay, because again, it's a triangular shape, so that's the way that we get to that. So that's our 1/2 of delta. That's our external work. Our internal work is done exactly the same way as what we did before. Okay, that it's MP, so I've got three hinges that formed, an MP here times theta 1 plus an MP times theta 1 plus theta 2 plus an MP times theta 2, like that. So it's the exact same equation that we had before, except now theta 1 is now 2 times delta over L, because the length from here to here was L over 2. We're using that parameter right there. And delta 2 is the same thing. Okay, so if I do the algebra and plug in like we did before, MP times 8 delta over L is now my internal work that's happening on here. So there's W internal right there. Okay, and then we basically set internal equal to external. And so I take Wn times L times 1/2 of delta is that term, and I set it equal to MP times 8 times delta over L. Again, the deltas cancel. That's how you know you're doing it right, if the deltas knock each other out. And then I can solve for MP for a distributed load. And so MP is equal to Wn L squared over 16 would be the plastic moment required for a distributed load of Wn. Okay, now you got to kind of watch the units on this a little bit. Normally we work these in kip feet. Okay, so L is in feet, and this will be in kip feet, and this MP will also be in kip feet. Okay, the one thing that you've got to kind of watch for that, so if I watch my units, WN is, a KLF, and L is a foot. Okay, the one problem you're going to have when we go in and do that last substitution is this guy is in KSI. And so there will be a units conversion that has to take place here to get the units to line up. Okay, because this guy is going to be measured in inches cubed, right? So really what we have to do in all of this is one of the feet cancels the foot in the bottom of this. I need to multiply this then by 12 inches per foot to be able to get to a true Z value. And that was the same for the other equation as well. Okay, so you got to kind of watch the units with what's going on here, but the same approach is still sound on what we're doing there. All right, so that's how you get the plastic section modulus for a distributed load on a fixed beam. Okay, all right, so that's kind of the basics. All right, now let's take a look at what do you do with continuous beams. Okay, suppose I have something a little bit more complex. Okay, and the problem with this one, now I have a continuous beam. They're all the same span, 15 feet, 15 feet, 15 to the load, and then 15 more to the support, and then 15, 15, 15, 15. It's all the same spacing. The loads are at the middle of all the spans. The load here, PN, and then I have 1.5 times PN in the middle span, and then I have PN back over here. Okay, the problem that we have with doing this plastic analysis, this plastic hinge mechanism, is we don't know which one is going to happen first. Okay, so what you have to do is you have to analyze all of them, analyze all of the failure mechanisms. All right, and so that's what I'm going to do. I'm going to start with the first span, AB, and I'm just going to say, well, if he's the one that controls, then this is what will happen. I have a real hinge here, so there's no work required to make that one behave like a hinge because it already is. And then I have to form a hinge under the load, and then I have to form a hinge over the top of the support, and that's my 3 hinge mechanism for this first bay AB. Okay, and you go solve it the exact same way. Okay, and again, depending on where that load is, it's at the middle, so my theta 1's on the left, or I'm going to call this displacement as delta 1, and then theta 2 would be the rotation on the other side, and then of course the angle that this big hinge goes through is the sum of the two, theta 1 plus theta 2. Theta 1 is delta over 15, theta 2 is delta over 15, okay, and so I can plug all of this in. The external work is Pn times delta 1, so that's no different than what we did before, and the internal work is then Mp multiplied by the rotations of the locations where the plastic hinge is formed. So it's this guy times theta 1 plus theta 2, and it's this guy times theta 2. So again, we don't have the first term because it was a real hinge happening there. And so if I plug in delta over 15 in for all of this, I get MP is going to be delta over 5 for that. And then I set these two guys equal to each other. That's what I did here. And now I can solve for Pn as being MP over 5, which is equal to 0.2 times MP. Okay, now again, I could rearrange this and it could be, MP is 5 PN, it doesn't matter, but what we're going to look at is the load here that it can support is 0.2 times the plastic section modulus. Okay, now this span for AB is also the same thing for DC. It's the exact same, but only in reverse, right? I have a real hinge here, I would put a hinge underneath this and underneath this, so we're just going to say that these two guys would fail at the same time at a load equal to 0.2 times MP. But let's take a look at what's happening in the middle span. Okay, now the middle span, because it doesn't have those real hinges on the ends, I have to form a 3 hinge mechanism on this. All right, and so there's a hinge that forms over this support, one under the load, and another one over that support. And we'll write everything the same way, except we're going to call it theta 3 and theta 4. The angle that this middle hinge goes through is theta 3 plus theta 4. I'm going to say that this load moves through a displacement that we're going to call as delta 2. Again, I don't know the values. I don't really care. Okay. Write your expressions for theta 3 and theta 4 in terms of the delta. So that's delta 2 over 15 and delta 2 over 15 for the other one. Same as what we had in the first one because the loads are in the same location. Okay. The external work then is 1.5 PN multiplied by delta 2. The internal work then is now I have 3 hinges. And so it's going to be MP times theta 3, that hinge, plus theta 4, that hinge, plus theta 3 plus theta 4, this hinge. And so I get all 4 of them back on this. And so if we set those two equal to each other and I solve for Pn, you'll get an expression that says that Pn is equal to MP over 1.5 times 4 over 15. That's the math. And we do a little bit of simplification. This is 8 over 45 times MP. And so this mechanism forms at a PN load of 0.178 MP. Okay, so now you've got two answers. I have one that is 0.2 MP and one that is at 0.178 MP. And so the way you ask yourself this is which one occurs first? If you start at zero load and you slowly ramp up PN, I'm going to reach this one first. Okay, and so this is the one that will fail first. So that middle span under this load, this 1.5 PN, this is the span that controls. And that's one of the things that's cool about these analysis techniques is now you can tell me where, which mechanism is the one that's the controlling mechanism. So if I have a weakness here, I could do something to beef up the beam in this area. Maybe I reinforce it with some plates on the flanges, or I, add, up the size of the member in that location. I can start to control things, but that's the information, the kind of information that as a structural engineer that we need to worry about. But that's how you get to PN for this value. And then I can take this formula and just like you did before, you can rearrange this and set it equal to ZXFY, and now you can solve for the required section modules to hold this thing up. Okay, now the one thing that we did assume in all of this is that we assumed that ZX was the same all the way through, that MP was the same all the way through. If that's not the case, then you have to play with different ZXs, but again, you're just modifying these formulas and kind of playing the game that way. All right, so that's kind of how you can handle continuous beams. You have to consider all of the spans. Okay, now there's one other little one that we're gonna briefly touch on. We won't do much of it in this class, but what do you do if instead of a single point load, well, here's the rearrangement of that formula. Sorry about that. So my PN is 0.178 MP, and I set that equal to 0.178 ZXFY. I can solve for the ZX required. It's 5.62 times PN all over FY. Again, watch your units. This is kips, this is inches. Okay, there is an implied foot hanging around in this thing with the 15 feet, so you got to kind of watch that, but in general, that's what we have. All right, so now on to our last one, and that's this multiple concentrated loads. Okay, what happens if you have a beam that is fixed on one end and hinged here and has 2-point loads? Well, now the problem is before we're still looking for a 3-hinge mechanism, but we don't know where the hinges are. Okay, more than likely I'm going to get one at this is a freebie. That's pretty much a guaranteed hinge. And this other wall support could be, but it may be not. Depends on the section properties and the loads and a whole bunch of other factors. So you have, in this case, multiple cases that you have to look at. The first one assumes a hinge forms here, a hinge forms under this load, and then I get the freebie over here. And I would do this mechanism and do the exact same analysis and find out what the PN value is for that. Okay. The second possible mechanism is that it fails here. It fails under the second load and it fails here. That would be this case, and you analyze it exactly the same way. The next case, though, that could happen is maybe this guy's super strong. Maybe instead I hinge it here and I hinge it here, and then I get the freebie over there. So that would be a case that you would have to analyze, and you would go through the same process. Notice I've called everything a different delta. This is delta 1, this is delta 3, this is delta 5. All my angles are different. You have to apply the same principles that we just showed you for all three of these cases. Okay, but there is another one that could happen, and this is one that's in your textbook, in the McCormick textbook on this. And one of the assumptions that we can make is what happens if this one and this one form at the same time? Okay, well, if that's the case, well, then I can actually get a hinge mechanism that would exist such that these two displacements are exactly the same. Okay, what we're calling is delta 7 on there. And then I would get a distribution that looks something kind of like this. If I call this as theta 7, and it was flat originally and flat at the end, then the angle that this guy goes through is also theta 7. Again, I'm just drawing the line and continuing it, right? And likewise, if this thing is symmetric, which for our example, we said it was 10 feet, 10 feet, 10 feet, and then we had some different loads, 0.6 PN and PN, then on this case, theta 7 would be here because it's a symmetric pattern to what's here, meaning that this one is theta 7, and now you do the same thing, except now you have plastic hinge, plastic hinge, plastic hinge, real hinge. And you would go through the exact same internal work calculation that we did before. But this one, you start getting a combination of effects. And then the more point load you put on a span, the more possible combinations that you have to look at. So here we had 4 cases, right? If I had a third load on it, well, then I would get, it would be like 8 cases at that point. It basically becomes a function of the number of point loads squared. So this was 2 squared, and then with 3 point loads, it's 2 cubed, and so forth. And you have to identify all of these combinations to be able to kind of work this thing out. So that's the basics of our plastic hinge mechanism and how we're going to be looking to calculate the plastic hinges and be able to come up with some sort of design practice. Okay, now AIC allows you to do this. I'm going to show you the alternative way here in the coming videos. where we're going to look at some basic AISC formulations and look at the code. But this is a very cool mechanics-based approach for, using virtual work or work energy to be able to come up with a methodology to actually size a beam or figure out what the limiting load is on a beam. Now, one thing to also point out is we have no factors of safety anywhere on this thing. I don't have reduction values. I don't have 1.2 dead, 1.6 live. We don't have any of that. So, if you were to truly want to work this problem, you would probably want phi and p in the formula up here, and then this you would probably want to play the game with pu. Okay, and that would be a way that we could apply AISC principles to this. But just the general formula, this is the way that we start to set it up. So I hope that's made sense to you. As always, if you got any questions, leave us some comments down below, and I'll be happy to answer them. Otherwise, if you found the video useful, please toss us a like on that, and then subscribe to the channel, and we will see you all next time. Happy engineering.